Hi, welcome to video 2 for lesson 3.1 on continuous random variables. This video is going to look at mathematical expectation and moment generating functions when we're working with continuous random variables. These are going to be very similar to the ideas that we used with discrete random variables, but we are going to extend them a little bit. Instead of using summations, we are going to need to use integrations. They're a little bit more calculus intensive. The first of the special mathematical expectations that we looked at with discrete random variables was the mean, and we'll look at the mean for a continuous random variable also. We still use the notation mu for the mean, and it's the expected value of x. The difference is that instead of taking x times f of x and adding it up for all of the individual values of x, we're going to integrate over the entire support of x. So we have the integral from negative infinity to infinity of x times f of x dx. Similarly, the variance of x, sigma squared, is the expected value of x minus the mean squared. And again, we're going to be integrating over the entire support of x minus the mean squared times f of x dx. Now, just as it was the case in the discrete random variable, that the variance was equal to the expected value of x squared minus the mean squared, it's also true for continuous random variable. And the standard deviation, sigma, is still equal to the positive square root of the variance in the continuous case. So let's look at an example. Suppose x is a continuous random variable with PDF given by little f of x equals 3x squared, and this is defined on the interval of x between 0 and 1. It should say that here, but I accidentally somehow erased it. We're going to find the mean of x. So mu, our mean, is equal to the expected value of x. We're going to integrate over the support of x times f of x dx. Now our support here is the interval from 0 to 1, so we're going to integrate from 0 to 1. X times 3x squared dx. If we work through this integration, we get 3x to the 4th over 4. We're going to evaluate at 1 and 0 and subtract. And that gives us a mean of 3/4. Now let's take the same continuous random variable and find the variance. We're going to use the formula. The variance, sigma squared, is equal to the expected value of x squared minus the mean squared. We just found that the mean was 3/4, so this is the expected value of x squared minus 3/4 squared. So we need to find the expected value of x squared, which we find by integrating over the support from 0 to 1, x squared times 3x squared dx. This gives us 3x to the 5th over 5. We're going to evaluate at 1 and 0, subtract, and it gives us 3/5. Now to find the variance, we're going to take that expected value of x squared, which is 3/5, and subtract our mean squared. So we've got 3/5 minus 3/4 squared. And if we do some simplification, you can see that our variance is 3/80. So let's take a look at moment generating functions for continuous random variables. The moment generating function, m of t, is still equal to the expected value of e to the tx, if it exists. So for continuous random variables, again, we're integrating over the support of x. So the moment generating function, m of t, is the integral over the support of x of e to the tx times f of x dx. And the moment generating function exists if the integral is finite for some interval around 0. It is still the case when we're working with continuous random variables that the mean is the first derivative of the moment generating function evaluated at 0, and that the variance can be found by taking the second derivative of the moment generating function evaluated at 0 and then subtracting the mean squared. We'll take a look at one more example. Suppose that x is a continuous random variable with PDF f of x is equal to x times e to the minus x for all values of x that are from 0 to positive infinity. We want to find the moment generating function for x. So the idea here is our moment generating function m of t is the expected value of e to the tx. We're going to integrate over the support, so from 0 to infinity, e to the tx times our f of x, which was x, e to the minus x dx. And if we do a little rearrangement, this is the integral from 0 to infinity of x times e to the minus x times 1 minus t power times dx. Now, since we have an integral that we're trying to evaluate at infinity, what we're going to need to do is evaluate this as a limit as b approaches infinity of the integral from 0 to b of x times e to the minus x times 1 minus t power times dx. And this integral is one that can be solved using integration by parts. If you recall integration by parts, the formula that we use is that the integral of u dv is equal to u times v minus the integral of v du. So we need to pick a portion of our integral here to serve as our u, and we need part of it to serve as our dv. So we choose u equal to x, and we choose e to the minus x times 1 minus t power to be our dv. And now if we want to, we need to find du, and we need to find v. So we differentiate u to find du, so it's going to give us dx, and we're going to integrate dv to find v. You may want to take your time and work through some of the details yourselves. So now this is going to be equal to the limit as b approaches infinity. We have our u, which is our x here, times our v, 1 over 1 minus t, negative, times e to the minus x times 1 minus t power. And we're going to evaluate that limit as b goes to infinity. Then we are going to subtract, and now we have our integral of v du. We pull out the negative 1 over 1 minus t and have the integral from 0 to b of e to the minus x times 1 minus t power dx. We can rewrite this way and complete our integral. And now we have two limits here that we're working with. So let's look at the two limits. The limit as b goes to infinity of e to the minus b times 1 minus t power minus 1. This portion goes to 0, so the limit is going to be minus 1. The other limit that we have as b goes to infinity of b over e raised to the b times 1 minus t power. That's 0. So what we have is we have this negative 1 times minus 1 over 1 minus t squared. So this is going to be a positive 1 over 1 minus t squared. And that's our moment generating function. Now we'll finish up the video by just using the moment generating function to find the mean. Rewriting the moment generating function just a little bit more simply. Instead of 1 over 1 minus t squared, we can write it as 1 minus t to the negative second power. We want to take the first derivative and evaluate it at 0 to get the mean. We take our derivative, we have negative 2 times 1 minus t to the negative third, and then we take the derivative of this inside part, so that gives us our negative 1 here. Now we're going to evaluate that at 0, and we get a mean of 2. So as I say, the ideas are very similar. There is more calculus involved when we're working with continuous random variables, so you may want to dust off your calculus or look at some of your online resources for working with integrals, because we'll be using them a bit when we're working with continuous random variables. Thanks. Have a good day.